Hello, everybody. Welcome to the overview video for renal function. In this video, I'm going to review some normal physiological function of kidneys, a little bit of anatomy, and set you up for understanding the lecture when we start talking about alterations in renal function. So here's the overview. Kidney functions, I'm going to try to simplify this into three categories. There's regulation, there's removal of waste, and there's some hormone production. Regulation, what we're talking about here is the kidneys help us maintain the amount of water that we need in the body. Dr. Doig talked about this in the fluid and electrolytes chapter. So when we have too much water on board, the kidneys help us get rid of excess water. And when we don't have enough water, the kidneys help us reserve some water. Now, some water always has to go out with the waste for the waste removal part. But in the case where the patient is dehydrated, you know that they're going to be releasing antidiuretic hormone and aldosterone. That's going to help the body to retain water. Other regulation is electrolytes, and what I mean by that are the charged ions, sodium, potassium, calcium, magnesium, chloride, etc. The most important of these that we're going to talk about are sodium and potassium, especially potassium. And then remember when we talked about pH balance and we said the kidneys can help us manage the pH of the blood, this is that function. And the way that kidneys do this is if the blood is too acidic, if the pH is too low, the kidneys can pee out some hydrogen ions. If the blood is too basic, then we retain the hydrogen ions and get rid of the bicarbonate ions in the urine. Awesome trick. Okay, and then blood pressure, I put it here. It's related to holding on to more water to increase the blood pressure or release water to decrease the blood pressure. There's also release of a hormone called renin, which I'll get to in a moment, and that's related to managing blood pressure. Okay, when it comes to waste removal, the wastes that we're talking about, there's a bunch of different ones, but there are two in particular that we keep track of. The most famous one is urea. Of course, it's named for urine. Urea is produced when we break down proteins. You'll remember that proteins are made of amino acids. Amino acids are called that because they have an amino group on them, a nitrogen. And as we'll see in a few moments, the liver has to help out here to help us make the nitrogen a little less toxic and release it as urea. I'll get to that. A couple of other forms that also go out through the kidneys are ammonia and uric acid also. Another waste product, it's not super toxic, but it's a really, really helpful molecule to keep track of, and it helps us figure out how well the kidneys are doing. This molecule is called creatinine, and we'll talk about it some more later, but its most important characteristic is that it helps us assess how well the kidneys are functioning. And then just as an aside, a lot of our drugs get metabolized and we get rid of them through the kidneys. And then hormone production. There are a couple of hormones in particular that I want you to be aware of. One is renin. This is the hormone that's part of the renin-angiotensin-aldosterone system. So renin is produced and released in the kidney. And then the other one that's really important for you to know is erythropoietin, also known as EPO. As we'll see later in the semester, EPO is necessary for signaling the bone marrow that we need more red blood cells. Why it's produced in the kidney is anybody's guess, but it is produced in the kidney and it is released from the kidney. All right, so those are the main functions of the kidney. Let's review now a little bit about renal anatomy. you remember the gross anatomy. There's the outer cortex, that just means shell, the outer shell of the kidney, and then the medulla, the inner part of the kidney. And then if we zoom in really closely, we see a lot, like thousands and thousands of these structures called nephrons. So we're zooming in here to this structure, and I'm going to show you a different representation of this that's more like what you have in your lecture notes. But I'm going to walk you through this image, the color image. It's a little easier to see. All right, so we have a blood supply that comes to the kidney, and there are a couple of capillary beds that I need you to know. There's the initial capillary bed called the glomerulus. This is, it translates from the Latin, it was like ball of yarn. So it's this ball of capillaries here, and they're really leaky. And that's where we get a lot of the fluid that leaves the blood, so that the renal tubule, this part in yellow, can act on that fluid. That blood from the glomerulus is recollected into an arteriole that goes through a second capillary bed. Let me just point out, this is an unusual setup. Usually when blood goes through a capillary bed, then it gets collected and goes into a vein right away. So this is what's a little bit funny here. So first capillary bed, glomerulus, then recollected. Second capillary bed is this peritubular capillaries, and that's where a bunch of exchange is going to happen. Let me show you, this is the diagram. It's more like the one in your lecture notes. Same setup. Here's the blood supply. The first arteriole, the incoming arteriole, is afferent, and the outgoing arteriole from there is efferent. If you want to think, A comes first, entrance, shouldn't say entrance, coming in, A comes first, and then efferent exit, leaving the glomerulus. The peritubular capillaries all wrapped around there. The blood then gets recollected into a venule and then heads back towards the heart. All right, this is a diagram that's similar to one that's in your textbook, showing you a close-up of the glomerulus. We have, let's see, we are here. This is the ball of capillaries, and then there's this capsule around the ball of around the ball of capillaries. This capsule is what's going to capture the fluid that's going to leave the capillaries, the glomerular capillaries. This part, the capsule, it's sometimes you'll hear it called the glomerular capsule, or the name of the person who first described it, Bowman's capsule. It means exactly the same thing. It's a kidney structure or urinary structure. It captures the fluid and then drains that fluid down into the renal tubule. Here's a cross section through it. So we see there are the capillaries, and then there's the cells surrounding the capillaries. And so for something to leave the bloodstream, it's going to have to pass through the cells of the capillary and pass through the cells of this capsule to get into this space and get processed. Let's see. All right, so here's a simplified version of the diagram. In red, these are the blood carrying structures, and in yellow, these are the urine related structures. Okay, so incoming blood is traveling in the afferent arteriole, brings the blood to the glomerulus. It goes through this capillary bed. It's represented here like a smooth ball. You know, it's a bunch of little capillaries. Those are really leaky, let some fluid out. And then the blood that's leaving the glomerulus gets recollected in the efferent arteriole and passes along to the peritubular capillaries. Now it's represented here as if there's a huge amount of space between the capillary and the renal tubule, but these are actually, they can like flush up against each other and to facilitate exchange that we're going to see. All right, let's take a look at the yellow structures. So again, this is the glomerular capsule, same as Bowman's capsule, same thing. Its job is to capture the fluid that's leaving the capillaries. And then the renal tubule is represented here as a straight line. You know, this is a little more complex than that. Part of it is really twisty, so it's called convoluted tubule. The part of that convoluted tubule that's right next to the capsule is called the proximal convoluted tubule. The part that's further away is called the distal convoluted tubule. And in between, there's this hairpin turn that is referred to as a nephron ansa. You may have learned it as the loop of Henle, and lots of people still call it the loop of Henle. Okay, so those are the structures. Now let's talk about the steps that the fluid goes through. So here are the specific physiological processes that underlie kidney function. This is at the top of page 2 of your lecture notes. So the first step, we've alluded to it, the blood is coming in through the afferent arteriole, comes to the glomerular capsule, to the glomerulus, and then some of the fluid is actually going to leave the bloodstream. When that fluid leaves the bloodstream with its solutes in it, that step is called filtration. So it's the diffusion of plasma across this glomerular membrane. And roughly 20% of the plasma actually leaves the blood at this point. And that includes the water of the plasma, along with small molecules like glucose. We mentioned this during the diabetes section. So some glucose is going to be leaving at this point. Electrolytes like sodium, potassium, magnesium, etc. Those are also leaving, and they get filtered here into the glomerular capsule. What is not leaving? Big structures like proteins. Now, individual amino acids can get out. The proteins are made of the amino acids, but once they're tied up into a big old protein, that shouldn't be getting out. And red blood cells, white blood cells, they should not be getting out through the glomerulus here. Okay, so this is filtration. Then a lot of what we just filtered, we're actually going to want to bring back in. And you'll remember from when we talked about diabetes, we said if the blood glucose is in the normal range, then all the glucose that comes out here into the renal tubule, all of that is going to get pulled back in. And that pulling back in, that's called reabsorption. And so there's some diffusion, some active transport, meaning you have to pay for it with ATP, is moving material from this filtrate that's here in the renal tubule back into the bloodstream. And so that includes things, some electrolytes like sodium, water, glucose molecules, as we've said. And you may be thinking to yourself, that sounds awfully inefficient. You know, you just filtered something out and now you're going to reabsorb it. Why would you do that? Well, it turns out that some of the stuff that we want to get rid of, it's just easier to get rid of it this way. That is, let it filter out and then pull back the stuff you want to keep. And as a way of thinking about this, I'm going to give you a couple of different analogies today. This first one is if you've ever tried to get sand out of your pocket or out of a bag, you could, pick out the sand, but it's easier to just, turn the thing inside out, dust out the sand and then, put your keys and your phone and your USB drive or, whatever it is you have in your pocket, put that stuff, the big stuff back in, the stuff that you want to keep. And that way you can get rid of the little stuff. Okay, so that's part of this filtration process is, getting everything. We can't do everything at once because it's blood, but we'll get out about 20% of stuff and then, bring back the stuff we want to keep. Okay, so that's reabsorption. Then the next step is referred to as secretion. This is the waste that's still in the blood that didn't come out in filtration step. We can actively pump that across, put that from the bloodstream, put that back, not back, put that into the filtrate. And things that get secreted are things like potassium ions, hydrogen ions, when the kidney is working at maintaining electrolyte balance and pH balance. This is part of when that is happening. And then finally, at the end, whatever is left here in this filtrate, that is what is destined to become urine and gets urinated, gets excreted from the body. So the filtered molecules that do not get pulled back in, and plus those molecules that get secreted, those are the things that get released in the urine. Here comes your second analogy. If you can think of this like you're cleaning out your closet, if you've ever cleaned out a closet, the filtration step is when you take stuff out of the closet. Now, with taking stuff out of the closet, you could, take everything out of a closet, but this is that's not possible with the blood. So what we can do with the blood is take out 20% of the little stuff, just dump it out. Anything that's 20%, like 1/5 of everything that's in there that's pretty small, just pull it all out. Now it's on the floor. Then we look through that stuff and put back the things that we want to keep of that 20% of stuff that's out here. Put back the important stuff. You got the towels and the sheets and the, whatever, I don't know, shampoo bottles, whatever you want to keep. And then we can look in the closet and see what else is still in there that I want to get rid of. And that's the secretion part. You're actively pulling out individual things and putting them on the floor. And then at the end, everything that stays on the floor has to go to the trash and then ultimately get put out of the house. That is what your kidneys are doing for you. So filtration first, that's pretty non-specific, just little stuff comes out, 20% of all the little stuff. Then we sort through that stuff and pull back what we want to keep. Look through the closet some more, see what is still in here that we don't want, pump that out, and then everything that's left in the tubule gets urinated out. That is kidney function. All right, now let's talk a little bit about how we assess normal kidney function. There's got to be a way to tell how somebody's kidneys are working. And so one of the clinical measures that we use is something called the glomerular filtration rate. This, ideally, we would have some way to get into all of those thousands, hundreds of thousands of nephrons and actually see how much stuff is actually coming out through the glomeruli. There is no way that we can actually do that. And so what we do is try to approximate how much fluid is actually coming through all of the glomeruli put together. Because the definition of this GFR, glomerular filtration rate, it's the volume of fluid that's filtered per minute by all of the by all of these nephrons together. All right, so let's put that in context. When the heart pumps, blood goes to all the different organs and all the different parts of the body. 20% of the blood, roughly 20% of the blood is actually heading to the kidneys. And I mean, the kidneys are not that big. They're not 20% of the size of the body, and yet they're getting 20% of the blood. And the reason for this is because it's not just about feeding the kidneys. It's also about like, okay, kidneys, here's some stuff that you can work on cleaning for us right now. And then 20% of that fluid, the 20% of that plasma is what comes out through the glomeruli. Okay, and And so when you add it all up, that is the net filtration. That's the glomerular filtration rate. Okay, so how do you measure it? Well, we approximate it with the measures of release of certain waste products. So there's this molecule, as I mentioned, creatinine. It's a waste molecule. For those of you who want lots of detail, this is FYI, but some of you may have heard of a molecule called creatine. Creatine is something we all have. All of our muscles have creatine. Its job is to help a phosphate group get put onto an ATP. And so for athletes that do kind of explosive kind of movements, weightlifters, football players, baseball players, that kind of, need all this ATP all at once. Some of those athletes supplement with creatine, but all of us, athletes, non-athletes, we all have creatine in our muscles, and its job is to put phosphate group onto the ATP. Okay. Some of that creatine breaks down every day and becomes creatinine. It's a small percentage of the creatine breaks down to become creatinine. Once it's creatinine, it's no good to us. It can't do that job of putting the phosphate group on. And so it's just a waste product. And we have to, we can get rid of it. So creatinine production is relatively constant, we've discovered, within a particular person. And it's closely related to how much muscle mass they have, so lean body mass. And as I've said, it is a waste product. So when the blood comes through here in the glomerulus, all of the creatinine that comes out in the filtrate, all of that gets excreted. Now notice that's opposite of what we had said, happens with glucose, where the glucose comes out and we say if it's in normal range, we're going to pull back 100% of that glucose. We're doing the opposite with creatinine. We're like, yeah, you're waste, just go ahead, we don't need to pull any of that back. Okay, that's what makes it so handy, a metric for figuring out how well the kidneys are functioning. Okay, so if the glomerular filtration rate decreases, so less fluid coming across here, that means less creatinine is coming across. That means more creatinine is building up. And so that's how we use this creatinine number. There's a relatively normal range for it. And as that number increases, it tells us something's wrong with the kidney. We're not getting rid of it. And again, the reason we monitor it isn't because it's so dangerous. It's just really helpful. I think of it as like eggshells. They're, it's trash. It's not dangerous trash, but if I couldn't see the trash, all I could do is, touch the trash and I could feel that kind of crinkling. I could keep track of, trash elimination by seeing how much, eggshells I have. That's the role that creatinine is playing for us here. All right, now the amount of creatinine that's in the blood, I've mentioned it's related to muscles, right? So it's going to be related to the muscle mass. Well, it's a tricky thing to try to figure out somebody's muscle mass. And so instead of just looking at straight up creatinine number, you'll hear something called creatinine clearance. This is generally calculated off of the plasma creatinine, but we throw in 3 other factors. And I'm including the formula here. This is generally calculated for you already on lab reports. But I wanted you to see what the 3 factors are that you have to, that play a role here. Let's see, it can be calculated. So creatinine clearance. We're going to take the weight of the patient. So the bigger they are, the higher the creatinine clearance is going to be. We're going to use this constant and subtract the age. So the older the patient is, the lower we expect their creatinine clearance to be. And use the amount of creatinine that's in their plasma. And then this is the other piece, their gender. We expect a lower creatinine clearance for females. Now, why weight, age, and gender matter is, again, it's related to muscle mass, and you're using these constants and these variables, the weight and the age, as a way of adjusting your expectation for how much creatinine clearance you expect for this patient. All right, I'm not going to test you on all these individual things. What I want you to get the idea of is the amount of creatinine in the plasma. What's normal is going to be dependent on the patient's age, the patient's weight, and the patient's gender. And so the creatinine clearance calculation allows us to make those adjustments. What is confusing about this is if you understand, if the kidneys aren't working right, that the plasma creatinine is going to go up. Everybody gets that. Where they get confused is creatinine clearance, which is how much of the creatinine is going out. That number is going to go down. So creatinine clearance goes down. That means creatinine, how much you're keeping in the, how many eggshells you have in the house, that's going to creep up. Okay. Another waste product, it's often reported, it's not as handy as you would expect. It's not as useful a measure for estimating kidney function, but you'll still see it on lab reports. This is, it's a measure of this nitrogenous waste called urea. Why they don't just call it urea, I don't know, but it's referred to as blood urea nitrogen, or BUN is the abbreviation. And where this comes from, where this nitrogen is coming from, is, as I've mentioned, the metabolizing of proteins. Now, if proteins are being used, if the amino acids that made up the protein, if you're going to use them to make another protein, you know, you took it from some actin and myosin that you ate as part of a meat, and you're going to use it to make some hemoglobin, then the nitrogen stays exactly where it is in the amino group on that amino acid. But if you're going to use that amino acid for fuel, or you're going to use it for gluconeogenesis, you're going to make sugar from it, then that nitrogen, that amino group has to come off. And that happens in the liver. So the liver takes off those amino groups and forms something called ammonia. It's a waste product. The problem is ammonia is really, really toxic, very damaging to our cells, especially to the central nervous system, as we'll see when we talk about liver function. So this ammonia, yeah, one, gotta get rid of it, but two, I need to make it less dangerous while it's still inside the body. And so it gets, a couple of ammonias get bound to a carbon dioxide to make this molecule called urea. Urea is still a waste product. It's just not as damaging as ammonia is. And again, I don't expect you to know the chemical formula for this, but for some students, it's helpful to see it. That it's basically these two ammonias get neutralized, put together, and made less dangerous. But again, urea is still waste. It's going to get from the liver, it gets put into the bloodstream, and then the kidneys have to get rid of it. So it's produced in the liver, filtered, and excreted by the kidneys. As you might imagine, if the glomerular filtration rate goes down, the plasma urea amount goes up. So plasma BUN levels go up. And you might ask, well, why don't we use that one to keep track of kidney function? And it turned, I mean, you can't, this number does get reported. The thing is, there are multiple other factors will influence how high this number is. So like protein intake, how much somebody's exercising, how much they're building muscle, all of that, all of those just different factors will make this number go up and down. So it's more variable than the creatinine is. And so you'll see this reported, you keep track of it, but really the better metric for kidney function is creatinine level and creatinine clearance. All right, with that, I will see you guys in lecture and we'll go over alterations to all of this normal renal function. See you then.